All right, so we're getting very close to our to being completed with our review of pre-calculus. We just have a few more things to go over. So when we're done with all this, of course, we'll dive right into chapter one, and we'll introduce the new material, which is in chapter one is limits. Okay, so this is a sort of an example left over from our discussion about quadratic functions. This is an application that, surprisingly enough, does require us to use a quadratic equation. We have a carpenter building a rectangular picnic table, and due to space constraints or restrictions, the length must be 2 feet more than the width. All right, so why don't we start by drawing this? All right, so here's our length, and here's the width. And of course, you recall that the area of a rectangle is the length times the width. Although sometimes it's called the base times the height, it means the same thing. Now they're telling us here that the length is 2 feet more than the width. Okay, so let's say that x is the width. That implies that the length is x plus 2. Now the area of this table must be 35 square feet. Okay, that's what they're aiming for. They're squeezing it into some area where they have exactly 35 square feet available to them, and they want to take full advantage of that. So what we want to know is what dimensions would satisfy these requirements. Now, this is a very simple problem. I mean, you could almost do it in your head just by looking at it, but it turns out, though, we can actually use or convert this into a quadratic equation and then solve for it either by using factoring or else the quadratic formula. So here's what's going to happen. First of all, we know that the area is the width times the length. By defining the width as x and the length as x plus 2, you can see that x times x plus 2 is, of course, x squared plus 2x. And we already know that the area must be 35 square feet. So we set this equal to 35, and then we rewrite it. We subtract from both sides the 35, and we end up with x squared plus 2x minus 35 equals 0. So surprisingly enough, we have a quadratic equation here, and we're about to solve for the solutions. Okay, so here we go, x squared minus minus 2x plus 35. And of course, this is what we're looking for, the solutions right here. This is where the function crosses the horizontal axis. The values of x at these 2 points, we'll call them x1 and x2, are the solutions of this equation. Well, now we just use our old friend, the quadratic formula. So once again, let me just quickly repeat this. So you can see that a equals 1. The coefficient of x squared is 1. Let me see if I can make that just a little bit bigger. There we go. Okay, so a is 1. B is 2, the coefficient of x, and then C, the constant, is negative 35. All right, so we just plug them in. And so you can see, even though it looks like a mess, under the square root sign, we have 144, which of course is the square of 12. And in fact, I'll just quickly remind you of some interesting notation here. When we have the squares of the integers, the positive integers, I should say, now, the key about these numbers here is that every one of them is a square of an integer, which implies that the square roots are also integers. Okay, and that should be pretty obvious. I mean, so in other words, 1, 4, 9, 16, 25, 36. What do they have in common? The square roots are all integers. So these numbers have a special name in math. These are called perfect squares. Okay. So a number like that. Now that means that 144, of course, is a perfect square because it's equal to 12 squared. And so what that means is that when you take the square root of a perfect square, you're guaranteed to get an integer. So you can see if after you do some algebra, what you actually have here is -2 plus and minus 12 over 2. And of course, this plus and minus sign means you're doing two things. You're taking the -2 minus 12 over 2 and -2 plus 12 over 2. And this reduces to -14 halves and 10 halves, or in other words, -7 and 5. Those are the two solutions to this equation. And if we go back to the graph, you can see that this point is where x is -7, and of course y is 0. And over here we have +5. Now, in a normal situation, in another situation, I should say, we'd be done. We'd have two solutions, but now this is a physical problem. And of course, it's not possible to have a width or a length that is negative. So that implies that the solution is right here. We can only use the 5 in this particular case because we can't have any negative areas. We can't have negative sides. And we can't have negative anything here. So that means we can discard this -7. It is not relevant to this problem. What does matter is that 5, though, does give us what we're looking for, because if you draw out your rectangle again, you'll see the width. If the width is 5, then the length is 7, and of course the area then is 35. Okay, so I thought you'd find that very interesting. It's an unexpected way of using the quadratic formula. Okay, and then what we also wanted to do in our discussion about parabolas is look for the intercept. The intercept is very straightforward because what is the intercept after all but the point where the parabola crosses the vertical axis, wherever that is. We know for a fact that at this point, x is 0. We don't know what y is, but we do know that x is 0. So in order to find this point, all we have to do is evaluate our function where x equals 0. And of course, these drop out, and we're left with the constant c. Okay, so it's easy. It's just like knowing when the curve faces up and down. That's easy because we just look at the sine of a. In order to find the intercept, all we need is to look at the constant. So like this one, for example, given that the constant is -35, we know that this intercept here is the point 0, -35. Oops. Okay. I guess we could go look at it in Symbolab if you want. Symbolab does such nice work with these graphs. We might as well. And it'll confirm everything we've just done. So we have y equals x squared plus 2x minus 35. And when we look at the graph, it'll show us everything we want to know. As we predicted, oh, okay, well, I guess I didn't draw it as well as I might have. Ooh, this is awkward. You see, I'm not sure. I would like to shift it up. I really, oh my God. Oh, here we go. I see. I just had to move it up. Okay, so here's the intercepts, -7,0 and +5,0, which is what we would have expected. The reason why this is so big I guess, is because, oh, here we go. Okay, that's much better. Okay. And then here we have the intercept 0, -35. Now, this is the minimum point. We didn't attempt to find that, but we could have if we needed to. And we know how that works. This is the vertex. We have the formula for H, we have the formula for K. And if we need the vertex, we can find it. All right. Domain and range. Now, what's great about these quadratic functions is that the domain is all the real numbers. There's no value of x where we might find division by 0 or an imaginary number. There's no asymptotes. So the domain is the entire real number line. The range, as we've already previously discussed, depends on whether the function is, or the parabola, I should say, is facing up or down. Okay, so for example, you recall that if A is positive, the vertex, let's say it's here, H comma K, H is equal to negative B over 2A, and K is f of negative B over 2A. And since this is the minimum point of the function, the range starts here and goes up to positive infinity. So that's why it's written this way, right? If you prefer, you can think of it as K up to infinity, including the K, okay? But for a negative, where the parabola is facing down, then everything works in reverse. So the formula doesn't change. HK, H is negative B over 2A. K is f of H, or f of negative B over 2A. That's the maximum value. And so the range ends up here and starts at negative infinity. Okay, so you can rewrite this if you want, like this. And notice how it's a square bracket because we do include the K. Okay, now let's look at a quick example. Here's a parabola which is clearly facing down. We don't have to worry about the domain. It's the entire real number line. We already know how to identify the fact that it is facing down. Also, we know that the intercept is -1. Sorry, I drew it backwards. It's 0, comma, -1. And then the domain. Now the range will therefore be everything from, oh, by the way, I just realized I haven't drawn this as well as I should have, because this may be the vertex. Sorry, this may not be the vertex. This is the intercept, but it may not be the vertex. So I'll tell you what, let's go to Symbol Lab. Let's just say that this drawing is not correct. I don't think I did it correctly. Let's try that with Symbol Lab. Minus 5x squared plus 9x minus 1. Here we go. Ooh, okay. Well, you know what? I guess it's a good thing that I didn't rely on my graph because it's clearly not correct. I mean, the intercept, sure, it is 0, -1, but let's see, the vertex is way up here. So sometimes it could be a little deceiving. Sketching, this is one of the reasons why having a package like Symbolab is so great, because sometimes it could be a little tricky trying to figure out what a graph might look like. And then here's our two solutions. You can see they're quite messy, but they were obtained from the quadratic formula. So for our purposes right now, what we're actually after, though, is this right up here. In other words, since this is the maximum, the range is everything from negative infinity up to, as you can see, 61 over 20. So how did we find that? Okay, so parabola is facing down. So we know that the range is everything from negative infinity up to the vertex, which is f of negative b over 2a. And so remember, in this case, a is -5, b is 9, c is -1. So h is equal to negative b over 2a. So when you plug those in, you get -9 over 2 times -5, or positive 9/10. And then, of course, k is f of then 9/10. Now that's a little tricky to solve for. Here it is. So we got -5 times 81 over 100 plus 81 over 10 minus 1. So of course we're going to need common denominators. Now you multiply this one out, you've got -405 over 100 plus 81 over 10 minus 1. What we're going to need to do is use 100 as our common denominator. So let's multiply this expression by 10/10 and this one by 100 hundredths. So we've got -405 over 100 plus 810 over 100 minus 100 over 100. And that ultimately leaves us with 305 over 100, which reduces to 61 over 20. So the vertex is 9/10, 61 over 20. And of course, that's exactly what Similab told us. All right. And that of course, the whole point of all this is that means the range is everything from negative infinity up to and including 61 over 20. All right, so we're going to look at a few other types of functions very quickly. A power function looks something like this, where it's a polynomial and it has the form a times x to the b power. And a and b in this case are not restricted to any particular values. Remember, with a polynomial, the exponent must be a non-negative integer. Here, with a power function, b can be literally anything. And then if we want to, I mean, we can determine if this is an even or an odd function. Remember, we did this the other day. Even means if the exponent is an even number, there's a very real chance that this is an even function. And if the exponent is odd, there's a very real chance that it's an odd function, although there's no guarantee. So this is what we're aiming for. All right, so this one, 3x to the 7th is an odd function because, as you can see, f of negative x is 3 negative x to the 7th, or negative 3x to the 7th, or you can think of this as negative f of negative x. Let's see. Yes, because f of negative x, all right, let's rewrite this. F of negative x is negative 3x to the 7th, which means negative f of negative x is positive 3x to the 7th, which is the original f of x. All right, there we are. We're good. Okay. Actually, if you're interested, why don't we see what this looks like on Symbolab? 3x to the 7th power. Now, as a rule of thumb, when we find odd function, there's a tendency for them to be symmetrical with respect to the origin. In other words, you can see what's happening in the first quadrant up here is a mirror image of what's happening in the third quadrant down here. This is what you normally expect to see with an odd function. Okay, the symmetry is between the first and the third, or possibly the second and the fourth quadrants. That's also a possibility. In fact, if I change this to negative 3x over 7, that's exactly what you'll see. Yeah, so now it's between the second and the fourth quadrants. With even functions, the symmetry is between the left and the right. Okay, so in other words, um, if this was 3x to the sixth, you would expect to see symmetry in the first and second quadrants. Exactly, right. Or if I change this to -3, then the symmetry would be between the third and the fourth quadrant. In other words, from left to right. Right, exactly. Okay. All right. Anyway, so like, oh, here's a good example, 4x to the sixth. So we've just proven here that this one is even because f of x equals f negative x. And then here's the graph. And you can see it is, in fact, symmetrical from left to right. Okay. Now we have the so-called rational functions, which are simply a ratio of two polynomials. And here's a simple physics example, which I think you'll like. Imagine the following scenario. This is something I'm sure you've seen before. A tank is filling with water at the rate of 10 gallons per minute. At the same time, though, sugar is pouring into the tank at a rate of 1 pound per minute. So they're creating some kind of a mixture. Sometimes you see this used for cooking. A simple syrup is basically water and sugar, which can be very helpful for certain types of meals that you might be cooking. But what we want to know is the rate at which the concentration of the sugar is changing. So initially, let's say that we had 100 gallons of water and 5 pounds of sugar. So we've got two functions of time. The water is starting at 100 and it grows at a rate of 10 gallons per minute. The sugar started at 5 and it grows at a rate of 1 pound per minute. Right? They're both minutes, right? And if you look at these carefully, it'll remind you of the the cost functions we looked at yesterday. But instead of having fixed cost and variable cost, instead we have the starting value of the water and the rate at which it increases in the tank. Okay. But it's the same idea. Conceptually, these are the same as what we did with economics. So we want to know the ratio of sugar to water. Okay. Let's say there's some ratio that we're aiming for. When we pour in all this water and sugar, there's some ratio that we need before we're done with whatever this product is. If it's a simple syrup, then we are waiting until the concentration is 50% sugar. For other products, it might be something else. Okay, so this C of t here, the concentration ratio, is defined as a rational function because it is nothing but the ratio of two polynomials. So let's say we need to know what is the concentration after 12 minutes? Well, initially, C of 0, the initial concentration is 5/100 or 5%. After 12 minutes, what we're going to do is evaluate both functions at 12. You just copy this here again. So in other words, C of 12 is 5 plus 12. Sorry, in the numerator, S of t is 5 plus t, which means S of 12 is 5 plus 12. And then in the denominator, water is 100 plus 10t. Okay. Whoops, I wrote them backwards. Sorry, hold on. Yeah, it should be 10 times 12, which means 17 over 100 plus 120. 17 over 220, whatever that is our ratio or concentration. And that turns out to be 7.7%. Now, if you really wanted to, you could rearrange this algebraically and solve for the value of T that is required for the concentration to be any specific value, like zero point 0.5. But here, all we wanted to know is what is the concentration after 12 minutes? Okay, for a rational function, the domain obviously will have to take into account that we can't have division by zero. So here, for example, we have to disallow t equals -10, although because this is a real world example, um, we can't have a negative time. So because of that, in this case, the domain is actually everything from zero up to infinity, including the zero. But that's only because of the application. Theoretically, this function has a domain that includes everything except -10. So the way the problem is defined, we're only allowing for non-negative times, and therefore the domain is simply zero up to infinity, which also implies that the entire concentration ratio, actually, we could probably draw a graph of this. Let's try this in Symbol Lab. Okay. Um, so C of t is 5 plus t over, sorry, 5 plus t over 100 plus 10t. Oh, okay. Every so often, Symbol Lab kind of loses its mind, and wow, I don't know what happened here. I've seen this before. I don't know what we can do about it. This is obviously not what we're looking for. I think it's confused by this C. I wonder if it would help if I change this to f of t. No, there's something wrong here. Um, unless, let's see if we zoom in, maybe that'll help. I don't know. I don't think so. I don't think this is right. All right. Well, anyway, um, here's one. The domain of this function is clearly everything except 3 and -3. Now, how do we know that? Because x squared minus 9 is the same thing as x plus 3 times x minus 3. Okay. So we have to disallow in the denominator for -3 and +3. So this one, I think Symbolab can draw this one. What is it again? X plus 3 over x squared minus 9. And what we'd expect to see is asymptotes. Uh, asymptotes. So the way okay, well, actually, what's interesting here is that the 3 is this asymptote. The -3 ends up giving us a hole in the function. It's not an actual asymptote. It's just a hole in the function. Okay, that little hollow circle is meant to indicate there's a discontinuity here. So x can't be -3, but it also can't be positive 3. Okay. So anyway, root functions, yes, where we have x raised to a fractional exponent. So just as a quick review, just in case we've forgotten, the square root of x is the x to the 1/2 power. The cube root of x is x to the 1/3 power, etc., etc. So we call these root functions. Oh, that's all we had to say about that. Okay. But now what we have to be careful about here is that when we have an even value for n, we're going to have asymptotes because we can't take, actually, I guess what I should say is not necessarily asymptotes, but there will be restrictions on the domain because we can't take this even root of a negative number. In other words, you can't take a square root of a negative number, a fourth root, a sixth root, or an eighth root, whatever. But with the odd roots, if n is odd, it doesn't work that way because we can take the cube root of a negative number, the fifth root, the seventh, et cetera, et cetera. So this will have a major effect on the domain and the range of our functions, whether n is even or odd, that is. This is our exponential. Now, this is something we're going to see a lot more of later on. An exponential function means that x is actually the exponent. This is something we haven't seen up to this point. And it does have some interesting behaviors. For example, let's say that we have 2 times, oh, I don't know, 1.2 to the x power. Let's try that. So you can see this is a typical behavior for an exponential function. It grows very, very slowly. Eventually, it crosses the vertical axis, and then it starts to increase like crazy. Okay, so here the domain is all the real numbers, but the range is only 0 up to infinity, not including the 0. Okay, and so, oh, okay, here's another example right here. 3 times 2 to the x is exactly the same idea. But, oh, by the way, in this case, a is thought of as the initial value of this function. It's actually the intercept, the vertical intercept. If x is restricted to being non-negative values, then this could be thought of as the initial value of the function, but it is actually the vertical intercept. And then b is actually 1 plus the growth rate of x. Okay. So in the example I just showed you up here, 2 times 1 plus 0.2 that means that 2 is the intercept, which we confirm here. No, it says 0, 1. Did I draw this right? Oh, no wonder I didn't type it right. What did I write? That's interesting. The vertical intercept means that x is 0. If I plug a 0 in here for x, this becomes 1. Not sure why it's graphing it like that. That's very strange. Oh no, but it even says here the intercept is 0, 2. Then how come the graph isn't showing that? Oh, you know what? Let me run the graph again. Maybe there's a no. Well, that's you see now here it says 2, 1.2. I don't know. Makes me wonder about Symbolab. I mean, they're telling us right here that the intercept is in fact 0, 2, which is what we're seeing here algebraically, and yet this graph is not following that. Wow, I'm getting disappointed here. But anyway, the growth rate of this function, if 1.2 is b, and b is 1.2, subtracting 1 from both sides, 0.2 is the growth rate, which means 20% per time period. Okay, so this is how you interpret these functions. And if you change the signs, you'll see how it affects the graphs. See, I think I have a few examples here. But anyway, here's a quick, simple example. Again, kind of a real world example where we're trying to compare the relationship between a linear function and an exponential function. So we have two paintings in our collection. Painting A is worth $100,000 and it grows in value at a rate of $2,000 per year. Okay, so this is like the cost function in the sense that we have a fixed amount and an amount that changes every year. So we could make the case that the value of A over time looks like this. Okay, and it's clearly a linear function. Now, painting B, on the other hand, it's initially worth $100,000, but it grows at a value at a rate of not $2,000, but 2%. Okay, so 2% per year. Now, how does that get represented? So the way it works with B then is that A is meant to be the initial value. B is 1 plus the growth rate. So because the growth rate is 2%, or 0.02, that means that B must be 1.02. So this is the function for painting B. And so if I put them together on the same axes, I've done that in Excel. And you can see the orange is the exponential function. That's painting B. And blue is the linear, that's painting A, by the way. Here's B, here's A. So you can see they started out at the same value, but over time, painting B is clearly growing more quickly than A, and the spread between them is growing over time. Okay, so this is a good example of the relationship between a linear and an exponential function. Sometimes what we're trying to do with these problems is solve for the growth rate, and that can be done in a very straightforward way with algebra. So here's the biology. I guess this is from the field of biology. 2006, we had 80 deer in a wildlife refuge. By the year 2012, that population had grown to 180. If we're assuming that deer growth is exponential, what was the growth rate in this case? Okay, so basically, what we have here is 2 points on an exponential curve. And we're going to use those 2 points to solve for the growth rate. Now, here we have to be careful, though. We're going to think of this as a function of time. The growth of the deer population is a function of time. Now, it isn't such a huge deal, but here, rather than writing f of x is ab to the x, we want to make it clear that we're trying to model the number of deer at a given point in time. So we're going to rewrite it slightly. N of t means number of deer at time t. T, of course, is replacing x. But what we also will do is, rather than using the actual years, t equals 0 is meant to represent the initial time. And 6 would be 6 years later, because 2012 is 6 years later than 6. Okay, so we know the initial deer population is 80. We also know that in 6 years, it is up to 180. So how do we know what the growth rate is? Okay, well, the first thing we note is that n of 0, n of 0 is the same thing as a, the initial value. And we know that n of 0 is 80. Okay, so that gets plugged in here. We also know that n of 6 is 180, and that in turn equals ab to the 6th, or 80b to the 6th. So that means that 180 equals 80b to the 6th. And now we just solve for b, as you can see. We do some algebra, we divide out both sides by 80, and then here what we've done is we've taken, oh, sorry, it's 2.25. In the next slide, we're going to take the 6th root of both sides, and we end up with 1.1447. Remember, b is 1 plus the growth rate. And therefore, 1.1447 is 1 plus the growth rate. And then if I subtract 1 from both sides, 0.1447, and that can be interpreted as 14.47% per year. So that means that, based on the assumption that the growth rate is exponential, it works out to 14.47% per year. Interesting. Now we have another similar example. This time we're looking at the value of the coin and how it changes over time. So once again, we'll use this notation. Actually, no, sorry. This time we're going to change it again. Instead of number of deer, the value of the coin is what we're after. So what are we being told? It's a silver dollar minted in 1899, which, of course, at that time, its value was $1. So V of 0 is 1. In 2019, 130 years later, 120 years later, the coin is worth $37.42 to collectors. Now, of course, you know that all American notes and coins are always legal tender. If I took that silver dollar into a bank, they would give me it. In principle, they should give me $1 for it. And I get $37.42 from the bank. I'm going to get that from a collector on eBay, let's say. But in principle, I can spend any note or coin that was ever issued by the US government at whatever it says on that note or coin. So here's the values that we have, and you can see this is V of 120, V of 0, T is 120 years, and we're doing the same thing. We're solving for B. Now here we're going to take the 120th root of both sides, and we have 1.071, which means that the growth rate is that minus 1. Okay, so it's 7.1% per year over that interval. Now, what's the opposite of growth? We also have the concept of continuous decay. Okay. Now, you can write this in many different ways. Here we're using this formula, which is really refers to the rate at which either interest can grow over time or else the value of an asset can decline due to depreciation. But here we're going to use it for a physics example. And you can see that clearly this is an exponential function because the variable is t, and that's in the exponent. R is some constant or other. So just imagine that we have radioactive element, let's say it's uranium, which decays at the rate of 5% per day, which simply means that that amount of uranium is being converted into lead. Okay, so we start with 100 grams of uranium. How much will be radioactive after 10 days? So P is the initial amount of uranium. R is instead of the growth rate, it's now called the decay rate. Okay, notice that's how much the value goes down. And then T is just time. And so you can see that after even just 10 days, there's only 6.0653 grams left that is still radioactive. So the difference here is that the exponent is negative. So this one is exponential growth. And then this formula would be for exponential decay. Now, if you remember how the graph looks for exponential growth, exponential decay would look something like this. Okay. And in fact, why don't we just plug this into Symbolab? What do we have? PE to the, actually, it's 100E to the minus 0.5. 10 times 0.05 is 0.5, negative 0.5. All right, let's take a look at this. See, yeah, this is, I think, oh, I know what happened. I left out the variable. Sorry, the T, there should be a T in there. I was starting to get nervous there for a minute. There we go. It's exactly what we would have expected. Now we're going to quickly run through logarithmic functions. You recall logs from your travels. So let's say, for example, we are told that y equals 10 to the third power or 1,000. We can define the log. The log will give us the exponent, depending on what base we choose, of 1,000. Okay, so in this case, you can see we have a base of 10. So the log to base 10 is 3 because 10 to the third power is 1,000. So think of the log as providing us with an exponent. Or log base 3 of 9 is 2 because 3 squared is 9. Log base 2 of 8 is 3 because 2 cubed is 8. Now, in general, y equals log base b of x is equivalent to saying that b to the y power equals x. So for every logarithmic function, there's an equivalent exponential function. one can always be converted to the other. They mean the same thing. So sometimes it's more convenient to use logs and sometimes exponentials. The domain of the log is 0 up to infinity, not including the 0. And the range is all the real numbers, because no matter what the base is, the function will look something like this. Okay, in other words, the log of 1 is 0, no matter what the base is. Since b to the 0 power equals 1. Okay, so regardless of the base, the function will look something like this. I mean, the slope of it will depend on what the base is that you've chosen, but the basic curve is exactly the same. Now, if you remember, when you were in high school science classes, you often ran into the log base 10. That one is referred to as the common log. Okay. Because let's say, for example, you're studying earthquakes, you know that the Richter scale is a logarithmic scale based on log 10. So that means an earthquake of Richter scale 5 is 10 times as bad as log 4, because a Richter scale of 5 means 10 to the 5th power. A Richter scale of 4 means 10 to the 4th power. So we often run into these. By the way, if you look at your calculator very carefully, depending on which one you have, chances are there's only 2 logs on there, log 10 and ln, which is, we'll see in a second, natural log, which is log base e. Now, the reason why they only give you these two is because we can convert them into each other with a simple transformation formula, which I'll show you in a bit. You don't need all the others, log 2, log 7, because first of all, they're not used all that often, but second, because if we need them, we can derive them from other logs, like log 10. In fact, I'll tell you what, while we're on this subject, maybe I'll go find that formula for you. Here it is. Also, keep in mind, calculators only have so much room for buttons. I mean, there's a limited amount of real estate on there. So let's say, for example, you do something like this. You've got log. Now, this one would be 2, by the way, because 7 squared is 49. But if you want to calculate this from your calculator, what you could do is rewrite it as natural log 49 over natural log 7, or log base 10 of 49 over log base 10 of 7. It doesn't matter what the base is. Any base will do. As long as these are both the same, you'll get the correct value. It's the ratio that's always going to be the same. So that's why the calculators don't need, and even in Excel, which you may or may not be using, they're only going to have so many of them. But anyway, so the natural log, which is, by the way, the one you'll see most often in calculus. We don't run into log 10 very often. It's much more convenient to use log e, or natural log, for many applications. So you see it all the time in Calc 1 and 2. And in fact, the mere fact that they chose to call it a natural log gives us a sense of how important it turns out to be. We wouldn't call it that unless it was important. All right, you notice that the other logs don't even have their own special name. Like log 2 doesn't have a name, it's just log 2. But these get a name because they're so important. Now, here's some basic properties. The log of, no matter what the base is, the log of 1 is 0, because b to the 0 is 1. The log of b itself is 1, because b to the first power is b. So in other words, Um, Wait a minute, wait a minute. Sorry, let me fix that. Log E is what I meant to say. Okay. Now this is where it gets a little trickier. So I think having actual examples will help you with this. So these are the kinds of things you might want to try to remember that because they'll be awfully helpful as you go along in calculus. Okay. And we'll get a lot of practice with this is, don't worry, it's coming. But anyway, there are algebraic rules for logarithms. And again, this is independent of the base. You might recall that the log of a product is equal to the sum of the individual logs. Okay, now these are very helpful for reducing the complexity of an algebraic problem. You'll see when we get to that point where a lot of horribly complicated formulas can be reduced to something simpler just by applying logarithms. This is why, because of these properties. So, for example, the log of 100 is 2. We know that, but if you notice, you can decompose this into log 10 of 10 plus itself equals 1 plus 1, which is 2. Okay, because these are individually are equal to 1. Or this one, if you notice, by the way, you've got to be careful. You have to make sure that all the bases are the same. If you may have something like this, a very messy expression, and you can turn it into something much neater by writing it like this. Okay. Of course, you know that in math, we always try to make things as simple as possible or as neat as possible. All right. And then the fact that the log of the products, the log product is the sum of the logs, implies that the log ratio is equal to the difference of the logs. Okay. So you have something like this, which we can break up into a difference if it's convenient for some reason. And then we have the power rule, which is really useful because then we have the log of x to the n is n times the log of x. It's like here you can see that the log base 2 of x cubed is simply 3 log base 2 of x. Uh, And then here, for example, you can see the log. Now, by the way, this is meant to be an illustration of why this is working. Log b of x squared, we already know that we can rewrite that as, well, x squared is defined as x times x, but we know that this is equal to the sum of these individual logs, which means 2 times log of x. Oh, yeah, there you go. In other words, this is showing us why this rule is working. Yeah. And by the way, I just want to point out here that these three rules are not independent of each other. This one implies both the quotient rule and the product rule. They're all based on the addition product rule, sorry. It's not like they're three separate ideas. They're all directly related to each other. Okay. Like this one, for example, remember square root of x could be rewritten as x to the 1/2 power. So we can end up with simply 1/2 of log base 10 of x. Here we can split this up. You can see you've got both a product and a division going on here. So we can write it like this. And then on top of that, we know from the product rule, the power rule rather, that this term is the same as 4 log x. Okay. And then here, because we know that square root of x is the same as x to the 1/2 power. Ultimately, this becomes 1/2 log 10 of x. Now here, this one is a little trickier. This expression is the same thing as x to the 2/3 power. Okay, it's a little tricky. Because you can think of this as x over a to the 1 over b power. And when you have something like this, you're actually multiplying. And so therefore, this is equal to x a over b. This, yeah, you have to think about this one for a minute. 3 cube root of x squared actually is the same thing as x to the 2/3 power. Okay, this one, these are just some other quick examples. You can see we're doing the same thing. We're just rewriting them in a few different equivalent ways. And then our base formula is the one I just showed you earlier. Okay. So for example, the common log of 100 is the same as log 2 over 100 divided by log 2 of 10. And again, the base is irrelevant here. This could be for any base. As long as this number goes in the numerator, this is in the denominator, we're all set. And then here I've done the same thing, except I've replaced log 2 with natural log. It's the same thing. All right, now I just want to run through a few quick examples of solving equations with these properties. And then we'll wrap it up for today. And then the next time we meet, we're just going to have a very, very brief review of trig functions, and then we can dive into limits. Okay. I think you're eager to get started with the new stuff. So we're going to wrap it up today with what we're doing here. And then after a brief review of trig functions, then we can start with limits. All right. Anyway, so sometimes these properties can help us solve for much more complex problems. And so we have a couple of results that are known as the one-to-one properties, where, for example, here, b to the s power equals b to the t can only be true if s is equal to t. Okay, and you might think, well, how does that help? Well, wait till you see. Here, for example, imagine running across this equation and saying, oh my God, what am I supposed to do with this? Oh, wait a minute now. I know the one-to-one property of exponential functions. This tells me that x minus 1 must equal 2x minus 4. And now look how easy this is to solve. So x minus 1 equals 2x minus 4. I add 1 to both sides, and I ultimately end up with x equals 3. And on the next slide, we're going to double check and make sure that this is correct. Okay, so all you have to do is plug in 3 for x, and look what happens. Both sides are equal to 2 to the second power, or 4. So we must have done this correctly. Now, here's one that may not be obvious when you look at it. By the way, I just want to point out why this is working. When you have something like this, when you're confronted with this, what you're actually doing behind the scenes, based on the properties we just learned, or reviewed, I should say, we're taking the log base 2 of both sides, which are certainly allowed to do algebraically. And if you recall, so that just reduces to x minus 1 equals 2x minus 4. But it's just easier to think of this as a one-to-one property. In other words, this is what you're actually doing when you apply this one-to-one property. So it's nothing really mysterious. Now look at this one. You look at it and say, no, I can't do this one with the one-to-one property because I don't have a four on both sides. But yes, I do, because 256 is four to the fourth. Oh, okay. So now I see that I can use my one-to-one rule, and four therefore equals x minus five, and I end up with 9 as my final result. Very clever. All right. Now here's some examples. Like here, for example, now, if you remember, the quotient rule for exponents is this. And so here, this 3 is the same as 3 to the first. Oh. Okay. So in other words, this ratio, because it's the ratio, they both have base 3, I can simply write it as 3 to the 2x minus 1 power. And then all of a sudden it becomes possible to use that one-to-one property. Okay, so what I end up with is 4x minus 7 equals 2x minus 1, and that's what we have here. And now I just solve for it algebraically. Now logs have their own one-to-one property. Um, oh, actually, with logs, look what we can do here. We've got this horrible looking equation with two different bases. So why don't we try this? Based on the idea that, remember, we can convert any log base into another, let's take the log of both sides, the natural log. And so remember the properties we saw. This is the power rule for logs, which implies that here we have log 5 times x plus 2. Here we have log 4 times x. And now I can distribute these across log 5. So I've got x log 5 plus 2 log 5. This is a constant, by the way, equals x log 4. I subtract this from both sides, and this one. So on the left, I have two terms that are functions of x. On the right, I have a constant. So I can factor on the left-hand side. And now this is a constant. And of course, so with this. So I can just divide out both sides by this constant. But first, it looks like, okay, just to make it cleaner, not that it's really that important, but if you recall, of course, the quotient rule of logs tells me this. This wasn't absolutely necessary, but it looks nicer, I guess. And now I can divide both sides by this term because it is, after all, a constant. And I end up with this. Now that is a very messy expression, but it is itself nothing but a constant. Whatever that number is, that is my answer. Okay. All right. Now we're ready for the one-to-one property for logs. Well, actually, I'm sorry. I'm jumping ahead a little bit. This is another way we can solve equations with logarithmic properties. So now here we know that we can use the product rule. So what I'm going to do is consolidate these. And so, but you might say, well, okay, fine, but where does this get us? So let's remind ourselves. Aha. So what this is telling us is that, or this is the equivalent, the exponential equivalent of this is that 2 cubed is 6x minus 10. Okay. So actually, well, I don't need to do this again. So in other words, we have a logarithmic expression and we have the equivalent exponential expression. And so what we're going to do is rewrite this in the more convenient form, which is the exponential version of this exact same equation. These both mean the same thing. One implies the other. And now it's easy because you've got 8 equals 6x minus 10. 18 equals 6x. 3 equals x. And if you're not sure, you can just plug it back to the original equation and you'll see that it works. Now here's an interesting one. We have a little algebra to do. Now we end up with log x equals 2. We don't want log x, we want x. So how does that work? Okay, so starting out with log x equals 2. Based on this property, which is equivalent to saying that e to the log x equals x, what if I do this? This is my equation. I can take the exponential of both sides. E to the log x equals e squared. E squared is a constant. And remember, this is equal to x. So I end up with e squared. Okay. And if I had something like this, this is what my final result would be. Uh, okay. So again, we're using the properties of logarithms to take a messy expression and turn it into something much more manageable. Here's another one. First, what you should probably do is do whatever algebra is necessary to get the log or exponential on one side of the equation. Then we can apply our rules. Otherwise, it'll be a lot harder to see what you're supposed to do. And you can see here that we went from here. We took the exponential of both sides. We end up with 6x equals e to the 7 halves, or very simply, x equals 1/6 of e to the 7 halves. So finally, after all of that, I can finally show you the one-to-one property for logs. It's about time. Okay. So if the log base b of s equals the log base b of t, then it must be true that s equals t. Okay. And of course, this only is true if both of these are the same base. Let's look at some examples. Actually, I'll copy this property onto the next slide so you can remind yourself what this is all about. All right. So in other words, first of all, over here on the left-hand side, since these have the same base, this is my quotient rule. Okay, so we'll consolidate these just to make it simpler. And now, because we have the same log on both sides of the equation, I can just reduce this very nicely to and then the rest is just algebra. And that's it. And we have 10. All right. So that's that. So we're done with all of this good reviewing. And like I said, all there is left, I just want to do a brief, and I mean brief review of trig functions. We don't need to get too carried away with that right now. Um, the slides probably have more material than we really need. I just want to make sure we remember the basic definitions, and then when that's over, we can finally turn our turn our attention to limits. Um, I guess, the first week or so reviewing is normal. So that's where we are now. And so the next time we meet, like I said, I will then be quickly reviewing trig, and then we can at least start the limits. And in the beginning, like I said, there's some fairly complex sounding definitions, but once we start going through problems with limits, you'll see it's not that bad, or at least not as bad as the definitions make it look like. There's a lot of rules we need to understand, but they're not terribly complicated. There are special cases that are very messy, but we'll start with some very basic ones, and then we'll work our way up to the more complicated cases. And when limits are done, then we can turn our attention to what is really the most important topic in this course, which is derivatives. And so you'll see that derivatives themselves are defined in terms of limits. All right, so I think we've had enough for one day, so we'll just knock it off here, and I'll see you all next time.